When we built our broadcast segment, frankly, we really didn't care who became the DR or the BDR. We've got two routers on the segment, so not a whole lot to choose from. On a larger broadcast segment, you may want to make sure that one of your powerhouse routers gets to be the DR since there's a little more of a workload there. But the thing is, with the NBMA network that we're about to build for our OSPF network, we care a lot about who becomes the DR. And on top of that, we don't even want a BDR. More about that in just a moment. But here's the network we're going to use, 172.12.123.0/24. Frame relay, which is off the CCNA exam now, but we're going to run our OSPF on top of frame relay. And the reason I mention that is we have a PVC going from our hub router, which will be router 1, to both 2 and 3. Let me show you what that's going to look like. And with routers 2 and 3, those being spokes in a hub and spoke configuration, they are not going to have a dedicated channel between the two. So if router 2 wants to send anything to router 3, that's fine, but it is going to have to go through router 1. So that's something we have to watch as we create this particular network. Just to make things a little bit more difficult for me and to introduce some things later on, I've got a couple of different routers in here with a couple of different interface numbers. Router 1 is going to be running serial 10, router 2 010, and then finally router 3 is going to be using plain old serial 0. Sometimes I plant little things early on, as you may have noticed, to cause us trouble later so we can do some troubleshooting, but the difference in interface numbering here does not impact the lab. I just want to make that clear. So this is what we're about to build, and the key here is two of them really. First off, we want the hub to be the designated router. It has to be the designated router because in the segment connecting routers 1, 2, and 3, the only router that can get a multicast directly to every other router is router 1, because router 2 can't send a multicast over to router 3 since it has to go through router 1, and our routers do not forward broadcasts and multicasts. So router 1 has to be made the DR, and we don't want a BDR. And the reason for that is, in case our DR drops, what happens during that drop is that our BDR would take over, and we don't want that. We want to make sure that our spoke routers and our hub and spoke technology don't even participate in the election. So we got to kind of watch this, because it's not enough to make sure that router 1 wins. We have to make sure that routers 2 and 3 don't even participate. And to do that, what we'll do is set their IP OSPF priority to 0 on their serial interfaces. We're going to leave the one on router 1 alone, because you might look at it and think, well, I could go ahead and just raise it to 2 on router 1. Well, then it would win. But if router 1 drops later, then 2 and 3 are going to start trying to fight it out. You just don't want that. So it's much simpler, much more efficient to just go ahead and set it to 0 on your spoke routers. So let's go ahead and do just that. We're on router 1 right now, and you can see I just sent a couple of pings to the other hosts on the 123 network. Make sure we're good there, and we are. And what we will actually do is drop down to routers 2 and 3 first. The interesting thing with the priority command is that it is an interface level command. You're not going to do router OSPF 1 and then set a priority. So what we will do instead is IP OSPF priority, maybe. And then you see the values here. We can set the ranges 0 through 255. So we're going to set that to 0. And notice that I'm doing this first before I even configure OSPF on the segment. And that's it. That's all there is to it. So now routers 2 and 3 will not participate in the DR-BDR election on our frame segment. So what I wanted to run by you now, we have something else we've got to configure on router 1, because we're dealing with a non-broadcast multi-access network here. And I'm going to give you the theory, and then I'm going to tell you how it works in a real world, because I like to do that. What we've got to do on router 1 when we start the OSPF config is use a neighbor command to point to routers 2 and 3. And the official reason for this is that we're really simulating a broadcast model of OSPF over a non-broadcast network. Now that's the official theory, and that's what we're going to go with. In real world environments, especially in lab environments, I've noticed, you don't always need the neighbor command. I've seen hub and spoke OSPF networks work just fine without it. I strongly recommend that you use it for the exam. I just want to let you know, because every once in a while, well, more than every once in a while, I'll get a tweet from somebody that says, hey, I set this up. I didn't use the neighbor command. It worked just fine. Again, that's the real world. Theory says you got to have these neighbor commands on the hub, and that's where we're going to put them. Now, it doesn't hurt anything to put them on the spokes. They're just not going to do anything. They're just going to sit there. And one thing with Cisco exams and really computer certification exams in general, they tend to ask you to do a minimal config. Or a good practice exam question here would be of routers 1, 2, and 3, which ones require the neighbor command? Now, I've seen in both production and lab environments people put neighbor statements on the spokes. Again, it's not hurting anything, but they're not doing anything either. So again, for that exam, we want to have it clear. Neighbor commands go on the hub, and then on the spokes, we need to use IP OSPF priority 0. So let's go ahead and get things started up on router 1. We'll get our whole config started. Actually, let's see what iOS's help description of neighbor actually is. Neighbor, specify a neighbor router. That's really helpful. Specify a neighbor router, but that's what we're going to do here before we even start the config. And I'll point them at 172.12.123.2 and at 3. And now I'm going to start my network command. And again, we've got our wildcard bits here. Then our area, and we're going to stick with area 0. We're putting everything in area 0 so far. And that's it. Now, I'll run show IP OSPF neighbor. And remember I mentioned that attempt stage? This is the only place that you're going to see it. And that's on the hub as you're getting the configuration started. Usually, once we want the adjacency will take all of that dead time. It'll go down to the last second and you're thinking, I did something wrong, and then the adjacencies pop up. We'll see if that's what happens here. 2. And 3. Nothing to it. So let's go up here. And we still see it's probably going to be 1 minute and 8 seconds before those adjacencies come up. Pardon me. So what I'll do is just pause the video and wait for the messages to come up. And as usual, those adjacencies did come up at the last second. I was desperately trying not to do the elevator button thing where I just keep hitting it and make it work a little bit faster. But you can see that our adjacencies did come up from loading to full. And let's go ahead and run show IP OSPF neighbor here. And you can see now we've got 3 neighbor relationships, and this on router 1. And this is where you need to start being a little careful. And again, this little 0 here can be a little bit annoying, but it's the hangover, if you will, from fast Ethernet 0/0 with this font size. But I do not want to go smaller. So we see the neighbor IDs, and note that the one for router 2 is not a loopback. We might have a little bit of troubleshooting to do there. But also notice that for both of the new neighbors, the priority is set to 0, state is full, and both of them are DR others. That's exactly what we want, because if we had 3 routers on a broadcast segment, we would expect to have 1 DR, 1 BDR, and 1 DR other. But we want 2 DR others here on our hub and spoke network. All the spokes should be DR others. Also notice the dead time here is a lot bigger, and that's why. Because the hello time default on a serial interface is 30 seconds as opposed to the broadcast of 10. So 4 times 30, 120 seconds, 2 minutes. So that means you should never see one of those dead times dip below what value? 1.5 minutes, right? Because once that happens, all of a sudden the hello's not coming in. Maybe there's a little bit of trouble. Here's the address, the remote IP address through which we are forming the adjacency. And here finally is the local router, and you see that is 1/0. Coming up next, we're going to run some more show commands before we move on to the next segment, and also see what's going on with that neighbor ID. It's not broken necessarily, it's not harming anything, but we would like that to be 2222, and we'll see a couple of different ways to do that, and send some pings around. That's coming up next.